Yep. Hello. I'm Eric Robertson from Booz and Hamilton, and I'll be presenting on GeoWave. I know a lot of you got to see the little demo, 50-minute demo last night, so this will give you an idea a chance to digest some of the technical aspects of it. So hopefully that you'll find this engaging and a learning experience. So I suspect that everybody understands what a GIS system is, right? That's not new to people. I do this slide just because we get different varied audiences, and the key thing here is that we have a big data volume explosion and a technology growth. So, and we're really in that space of the data volume explosion, where we can answer an inquiry very quickly, such as on-click retrieval of data, like find me points of interest near me. So how do we leverage this big data? And there's been a lot of talks about distributing the workload across multiple servers, and we're playing into that BigTable architecture. So as a quick review, what BigTable is, for those that are not aware, it's basically a key value store, and so your keys are distributed over across multiple servers, and then those are then distributed into blocks across multiple data nodes. So and then each key is made up of like what we'll call row ID, and sort of a region, a column, timestamp. There might be also visibility constraints. And what we're trying to do here to achieve is that if your rows represent data that's in the same locality, then what you want to have is that particular row live on the same server with the same data and in the same data node where other data in the same locality is. So you have to have this data locality preservation conceptually on a map all the way down to physically on a dist node, right? So that's kind of the space we're playing in here. So the challenge here, of course, is that we have this row key, right, which is just a single ordered value, right? Where in maps you might have multiple dimensions, lat long plus time. And the presentation last night we talked about 5 dimensions where you had the source and destination, which you have 2 sets of lat longs plus a time element, so there's 5 dimensions. And yet we want to somehow distribute it on this single row key across multiple data nodes and still maintain that locality. So the basic problem here, and I'm going to focus on 2 dimensions right now, is how do we efficiently locate these vector tiles or tiles that resist in some intersecting bounding box, and then we have this BigTable architecture organized into blocks of sorted row identifiers, and we want to have this two-way mapping between these identifiers and this multidimensional space, these multidimensional constraints. So the way we solve it is using a space-filling curve. So the space-filling curve is I kind of think of as just a way of walking through your n-dimensional space, taking a line and walking through it. So I mean the fancy definition here is, of course, constructed iteratively. It produces a sequence of piecewise linear continuous curves, each one more closely approximating the space-filling limit. But in the end, you think of it as it's just a walk, a single curve where each discrete point in that curve is a discrete point or a cell or in a hypercube in your n-dimensional space. So it's ordered. So here I have on the lower left side in the red, you can see the curve starts 1, 2, 3, 4, 5, 6, 7, and it keeps going. So there's your order. And you can say locality-wise, well, 1's close to 2, right? The next part is that points close together, they share the same identifier. And then the bounding box over a region is really a set of ranges over this curve. So in that particular example, I don't know what those numbers are exactly, but probably like 76 to 99 might be the parts of the curve that intersect that bounding box. There's lots of different types of curves. In the prior example here, I showed there's 7 different ones here, and there's a way to, there's some studies on just deciding what the best curve is. I'm not going to go into too much detail the best one, but to give you an idea, about distortion of space. Of course, as you're walking through, you're going to have some places in the curve where the locality is not maintained, and I put up next to it a z-curve here to kind of get a point across. If you like, for example, just look at the middle. You see, if you look at quads, you look down the middle quad, you see these long stretches. So obviously, if you're jumping from one point to the next point, that's all. You're jumping, in this particular granularity, you're jumping half the globe. So that's obviously not maintained locality. Where on the curve on the left, which is the Hilbert curve, you can see that you're going to have a lot less of that. You still have some big jumps. Now, the precision of all these curves is determined basically by a number of bits you're allocating. And the example so far, I'll be using the 16 by 16 grid. So that resolution is about 22.5 degrees latitude, 11.25 degrees longitude. But the precision is can be adjusted, as you can see in the bottom. And so basically, the precision is based on the number of bits you assign to each dimension, and it's going to be square dimension. So you'll divide it up. Like if you're using a bit long and you have 2 dimensions, let's say it's 64 bits, then you might say 32 bits each. Will give you pretty sufficient, very, very granular curve. So to kind of give you an idea what a Hobart Index looks like, remember, going back to we want a row ID, right? That's going to go into our BigTable architecture. And so how do we compose this? And so the way it works is, if you can kind of think of it as like a quad tree, right? And so at the highest level, you have 4 quads. 4 cells, and so that one. So in this particular, on the left, we have the cell 1, 1, and then the next level we will have a cell 0, 1, and then drill down, we have another cell 0, 0. So each set of what we call interleaved bits, a group of bits by dimension, drills down that quad tree. Does it make sense? So to define these quadrants. So at any particular granularity, when we do a bounding region, the bounding region is going to cover different parts of the curve, right? It's going to the curve's going to kind of wind in and out of your bounding region, your query region. So what happens is, when you decompose a curve, given a query or bounding region, you're going to get a set of ranges, not just a single range, right? So in this particular example, we have 3 ranges, right? One thing to note here is that we're snapping to a grid, right? These if your query range is let's say is going to be some set of decimals or whatever, and you're going to snap out to a grid size. So your actual query range can translate it to complete these cells, and conceptually actually snaps outward. Now, the other nice thing about range decomposition is, especially with Hilbert, you don't have to necessarily, because it's a deep dive, and you continue to computate your ranges as you drill down. And so what happens in this particular case is, you might have different quadrants and different levels of cells you're navigating through when you're decomposing your ranges. And what will happen is, you don't have to walk through every single cell at that granularity. Right? You can skip whole regions because you can tell that the curve goes in and out. So we basically have the decomposition stops at a window when the quad is fully contained. All right. So that kind of gives you an idea of basically how Hobart works. And we're going to talk about some of the interesting problems we deal with when you're doing space-moving curves. The first one I want to talk about is intervals. And an interval would be like a polygon or multigon. So the idea here is, in this, I have this sort of a 66-cell polygon that's sort of a brownish color. And then I have this sort of query region. And you notice that the query region intersects that polygon. It's my blue query region. And you also know the polygon traverses through multiple cells, right? So a very simple way of doing this is to say, well, anywhere that polygon intersects the curve, any cell that it intersects, I'm going to just index it using the Hilbert ID for each one. So then you have these sort of duplicates, right? And then I know when I'm querying a subregion, the subregion is only going to look at the parts of the curve that it intersects, and of course it'll share some of the same cells, right? So there's a little problem with that, and the problem is if you take something like the Pacific Ocean at a really high resolution, 31 bits each dimension, then you're talking about 1.5 quintillion duplicates, so that's not desirable. So the way we've solved that is using a tiered indexing approach. As I mentioned before, you can drill down to different levels of granularity in the Hilbert curve. So basically what we're doing is we're creating tiers of these Hilbert indices, right? And each tier has a different level of resolution. So in the big blue polygon on the left there, that we'll probably do it, in this particular example, tier 2, right? And then the red one, we'll drill down to a lower tier, right? And then so that manages how many duplicates. So then the question is, well, basically what's your maximum duplicates that will allow, right? So I'll get back to that in a second. So basically, here's an example. So consider, let's see, got these misordered. That's okay. So how does this work with these polygons and this query range? So I got this query range in the orange area, and there's sort of a balance between these acceptable duplicates and false positives. So in this particular case, the point I'm making here is that query region intersects both the blue cells in the tier that the blue polygon is present, and also in a lower tier where the red polygon is. And so what will happen is when I do that query range, I'll find those polygons, even though they're really not present. So I have to do another filter to make sure that, in fact, they don't actually intersect. Just because at that particular tier they do occupy the same cell. Does that make sense? All right. So how do we manage the number of duplicates? And it turns out that in two-dimensional space, the cap is 4. And in d dimensions, the cap is 2 to the d. So why is that? And this is kind of a simplified perspective on how to see this, is if I take a very small polygon, and it can be infinitesimally small, and I put it right on the right on an elbow, a corner, right, intersection point between all these cells. It doesn't matter how far I drill down, how granular I get, it's always going to be on that intersection point between those quads. So I can never, ever get less than 4 duplicates in that case, unless I go to the top tier, which is the whole world, right, in that case, right, which is not desirable. Because then small polygons like this would all percolate up to the top tier, and then we'd have lots of filtering to go on, removing those removing those false positives. So I kind of talked a little bit about the multidimensional problem, and so GeoWave we've always kind of looked at as trying to focus on the more general problem. So what we're looking at is multidimensional numeric indices rather than just geospatial indices. We're looking at any sort of interval, not just polygons, but also time ranges. And we're also looking at another problem, which is unbounded indexes, which I'm going to talk to next, time being an unbounded dimension. So how do we deal with unbounded dimensions? So with light and long, it's pretty easy. We know the bounds. They're pretty confined. So with time, it's conceptually infinite. And even if you're using something like milliseconds from 1970, from 0 to how many bits you have in your long, it's still pretty extreme. So the way we handle that is we bin it. We create these bins. So basically, in this particular example, each year is our bin. And so for each bin, we have its own curve. So now, if you put conceptually two things together, we have a Hilbert curve index per each tier, right? And that manages our ranges, like polygons, and manages their duplication. And then we have Hilberts per bin. So it ends up, more than one curve is kind of the point here. And so the bin ID along with the tier and the Hilbert row ID, that all becomes the row identifier in your BigTable space. So you can see it, sort of hard to see on the left there, we have our index ID. And the index ID has the tier and the bin and the Hilbert ID. And then, of course, because we're storing an actual data item, we have all this stuff to the right that's actually the data ID, the data identifier for that particular feature. So here I'm going to kind of drill down a little bit of, well, how does this all work in practice? So I'm taking, like, say, a SQL query, and this one's using a D within. So I'm taking some point in space and saying, find me everything with 10 kilometers at this point, and color equals red. Well, the first part is I want to decompose that to ranges. So what happens is that D within is basically a circle, which gets snapped to a grid, so it grows to a square. And we then run Hilbert, run it over the Hilbert curve to find and decompose the actual ranges on that curve, right? And then we use those ranges to inquire to the tablet server. Tablet server figures out where the data blocks are for those ranges, and then goes and pulls the data for us. So on the right there, we've got our little circle, which is our D within, right? And then we have points that fall within it. We have a green circle and a red circle and another red circle. And you notice that one red circle is outside our query range, and then one red's in, and we also have a green one. So what will happen is, because they're all in that quad space, they all get identified, right? They're all within that query range based on the Hilbert index. So then we have to do an additional filter, right, to say, okay, you're really not in that range, so it'll eliminate one of the red ones. And by the way, you're also not the color red, so it'll eliminate the green one. Then the return is getting that single red item. But this is all happening on the tablet server. So the additional filtering is happening not in the client, but distributed over the multiple tablets. Right, so the client doesn't have to do any of this filtering. So a neat application is, I was just watching the talk prior to this, and they were talking about building tiles. And one question somebody raised, I said, well, why are tiles equal sizes? Why couldn't you have tile sizes that were determined based on the volume of density of that tile? And so, I mean, obviously having a strict fixed size tile makes some of the math a lot easier and management. So the question is, well, I would ask is, well, how can instead, knowing that tiles are fixed size and we have different densities, how do we efficiently construct that tile? And so this is kind of going to the example of distributed filtering that we just talked about in the prior slide. How would we do that with GeoWave? And we're using this concept called map occlusion culling. And the idea here is that at a particular pixel space, any one pixel might represent many items, because depending on your granularity, right? Many different features that appear within that pixel space. So you have this sort of pixel space comparing to actual real space, right? And the idea is that once you identify in that pixel space that there's something that exists, right, then you're going to color that pixel. And the question, and once you've done that, you don't have to continue looking for more items that result to that pixel, right? You've done it. You've said, well, I know there's one there. I can only show one, right? It's either there or not. Either there's a ton there, or at least one there, or nothing. So once I'm done, I can just skip on to the next pixel, right? Skip over all that data. So if you look at it from a Hilbert standpoint, well, how does that work? Well, I'm kind of traipsing along the curve there, and I bounce off and find at some elbow, oh, wow, there's a, and within the Hilbert space might be a much lower granularity in your pixel space. So let's say I have 1, 2, 3, 4 blocks there, and in the displayed pixels, each of those blocks, cubes, correspond to only the 4 pixels. But I don't need to scan all the corresponding features inside those. So as soon as I find one, I can basically skip to the end of the curve out and exit point of the curve for that particular cell, right? And start searching the next one, right? Make sense? So the idea is scan to the first pixel, seek to the beginning of the next pixel. And so from a standpoint of the rendering engine, this is all happening server side. The rendering engine is basically only getting the pixel results, right? So if you're 255, 256, you're talking 256 squared results back, right? I mean versus tripping through all the data. It could be massive. And yeah, so I talked about the distributed rendering part. So kind of gives you an idea of some of the theory behind GeoWave and how it works. Now I'm going to go over GeoWave itself and what it represents. So I kind of mentioned that our goal was to make something that was reusable beyond just geospatial applications. And some of the tenets and goals we set were make it a pluggable backend, make it modular design, and make the data self-describing. So one of the questions we will get is like, well, okay, now I know all this. How do I get data into GeoWave? So we have an ingest pipeline, and basically right now it supports Kafka topics, which is, for those people who are not familiar with Kafka, Kafka is a queuing architecture basically, and local files and also distributed files. And so we have a whole consumer ingest pipeline where you can have Kafka consumers, or you can have a series of local threads, or you can use MapReduce. And then, and you can see on the left, we support many different import formats. I'm not going to go through all of them, but you can see things like PDAL and grid formats, vector data, anything vector like shapefiles, GeoJSON. On the right, what's our destination? Well, GeoWave really is an index. It's a geospatial index using the Hilbert curve. So now you might have multiple kinds. So, for example, you might have data that has temporal aspects to it. And you might have that data temporal in two ways. So let's say you have two different dates, for example, maybe a start date and end date, or a creation date and update date. So you might have multiple indices, each one having a different dimensional constraints. So those all get populated at once. You can do your ingest configuration, say, these are the indices I want to populate. And it'll pipeline it in and do it all at once. And it also captures statistics and secondary indices. Secondary indices are things that don't fall into the numeric index strategies we're using, right? There'll be things like, maybe I want to index on words or color or whatever. So GeoWave, basically, most of the services come through GeoServer or GeoServer plugins, so that's where all OGC servers like WFS, WMS, that's our background playground. We have a couple of our own services on the side, things like image chip services, and we built a service for that in demo the other night on the taxi cab predictor, travel time predictor. So we have a couple, and we also have some administrative services to set it up. But most of our services go right through the OGC service from GeoServer. And I kind of mentioned Hadoop there. We have input and output formats. And that plays both in Spark and your MapReduce world. So some of the tested versions, just to give you an idea of the playground. For BigTable right now, Accumulo, that's our long-standing version. HBase is it's coming out like in nearly a day or two. It's really, really short. We're still making refinements in the newer one, but that's probably by the end of the week it'll be out there, with hope. And GeoServer, we've been running with GeoServer for quite a long time, so we support a long list of versions. We also support a whole bunch of statistics. I kind of mentioned that earlier. Statistics, are handy for, like, we do like histograms, cut-min sketch, hyperlog log, so you can do sort of cardinality checks on your data. And then we have a series of analytics that all run in MapReduce. Nearest neighbors, for example, clustering, density scan, clustering for everything. So we do two variants of k-means, and then we have heat maps, KD. So one thing that's interesting about nearest neighbors, I'll just take a second to talk about this. So nearest neighbors is interesting. I actually work with some people on different nearest neighbor type problems, and they're all, it's amazing how diverse they are. So what we kind of did there was we kind of built this unique infrastructure on the side, which is really just a playground to add your own. So for example, I'll give you an idea. One person came to me and says, oh, I want to be able to do optimal pylon placement. So their problem was, they have pretty, their data is not very dense, right? And they're looking for outliers where data is dense, right? They're looking for two pieces of data that occupy a small space, right? So in a low granular Hilbert curve, you might say, high resolution, I should say, you're looking at only two features occupying the same cell, right? And then there's the density scan basis type of nearest neighbor stuff where you're clustering, and then you run into something like OpenStreetMap or something where you have really, really dense regions. So I'll just give you an idea of roadmap of where we are. 9.1 is coming out this week. I kind of mentioned that. HBase is part of that. But we've done a lot. We've kind of grown a lot in the last, I'd say in the last 3 months, we've really grown. It's been a tremendous 3 months. We rewrote a command line API. That was a pain point for some people. Our documentation is getting better by the minute. One of the guys from RadiantBlue is spearheading that. Some stuff we've added, like field subsetting, if you don't want to get all your attributes from your simple features. We added this neat distributed aggregation framework, which is the foundation for the taxi cab. Thanks. And so the idea with that was, if people didn't see the demo, basic idea was I'm basically aggregating over tracks between all the points between two points, start and end, right? And I'm looking and aggregating them on the server side on a cumulo to get a result back to say, what's basically the statistics for prior taxi routes that have gone between those 2 points within a region of error. And so that was all done server side, and if you saw the demo last night, it was pretty quick. I mean, like seconds, and you were getting a response back over, I can't remember how many points it was, a billion points. It was quite a bit. So the aggregation framework, that's instrumental in making that happen. And so what's on the 9.2 roadmap? Well, I mentioned secondary indexing. And the secondary indexing is only partly there, right? It captures the secondary indices, and you can create on the side, but it's not integrated into the OGC framework. So if you were to do a query with a very large bounding box and said, with somebody's last name is Robertson or something like that, it wouldn't even use the secondary indexing, even though the idea of secondary indexing would be like, okay, well, my bounding region is really large, but there's only 2 Robertsons in the whole database, so I'll just use that instead. But that's not hooked up yet, so that's one other thing. And of course, we're adding more data stores. We don't want to stop at HBase, so we have a couple. I know somebody asked about Dynamo. I think that's going to be on a roadmap. I didn't put it up there, but I'm sure it'll come around. So just a quick, if I want to develop GeoWave, I kind of made a point that saying GeoWave is extensible, right? So it's if you have any multidimensional numeric index problem, then you might want to consider using GeoWave. So what's involved with adding your own dimensions, your own strategies. And this slide's really just point out that, well, in the end, if you have a data adapter which describes your data and how it's marshaled in and out of the BigTable architecture, and you can define your statistics you want. You can use the pre-can ones there, add your own, and then you have to define. I mean, that's pretty much it right there. If you just want to define a new data type, and this sort of describes how it plays in that universe, where your data type adapter describes the constraints it wants to use for indexing, and the statistics, and also what secondary indexing options you want to have. But as a developer, you might be interested in like different index strategies. Now I mentioned we do tiering, and I mentioned also that we have a binning, right? But you don't have to do that. You could just use if you, for example, know you're not dealing with intervals, and you're knowing you're not dealing with long dimensions, unbounded dimensions, you just might want, I just have point data. That's all I have. I just want a really simple, fast indexing scheme at one level resolution. Well, you can do that. And the other thing is load balancing. If you have struggles with load balancing and you want to do some sort of preset load balancing, then you can use a round-robin load balancing technique, and then you can mishmash all these index strategies together using a compound index. So anybody interested in looking at some of the code? Oh, one person. All right. Well, that's not a show of excitement for that. So, okay. Any questions? I got lots of other stuff, but I can. Yeah.
You mentioned the ability of importing raster data. I didn't see NetCDF on that list. Has that been considered?
We haven't actually had that conversation, but so I won't say it's. I'll say we haven't considered it yet.
Okay.
Anything else?
What's the distinction between index and secondary index?
Okay, so the question was, what's the difference between secondary index and we call them the other one a primary. So the primary is basically the space filling curve, and the idea is a multi-numeric dimensional index. Secondary indexing is anything that is I would say anything that's not numeric that you want to do, and that's one distinction. The second distinction is the primary index is storing the data with it, right? The only way we're going to get this data locality is if we store the data where we're indexing, right? So it's not like a traditional relational database model where you have your data in one table and you have your index in another. It's all co-located. So if you're an Oracle guy, for example, it's similar to the index organized tables, right? Secondary index is more like your traditional index. It's just a pointer it just has reference ID to the primary index, which is your space filling curve, right? So the idea is that you're going to do basically a hash join, right? So I'm going through my secondary index. If I'm traversing through it, I'm going to get those Hilbert IDs, those row IDs, and then I'm going to go look up the primary and pull the data. So naturally, you have to factor that in the cost and heuristic to say which index I want to use, right? And that's one of the reasons why the cost-based optimizer hasn't come out yet. Is it's tricky to get that right? So we're taking our time getting it right. And we just expose the interface, so if somebody wants to do secondary indexing, they can make their own determination and use it. But that's all.
Yeah, so I'm a developer on GeoWave as well. With NetCDF, I just want to answer that GeoTools is how we support raster, so anything that gets converted to a grid coverage, and NetCDF is supported by GeoTools, so it should work. I haven't actually tried it myself.
All right, so I just want to restate for the video that Rich Fetcher, he's the RadiantBlue developer and one of the key, I'd say he's one of the two major people that started GeoWave many years ago. And he was making this comment that NetCDF is something we'll support using a GeoServer in a nutshell. Right? It's a good summary?
Yeah.
All right. Another question? Yeah, go ahead. All right, nearest neighbor. So the question was index optimized for nearest neighbor search. So remember, the index is based on data locality. So I kind of mentioned there's an analytic for nearest neighbor. And the way I did the analytic was, in that particular case, since the nearest neighbor algorithm is looking over a large population, right? It's not looking at it. The question nearest neighbor is, we're not doing the stupid question saying, pick a point, find the neighbors. Pick a point, find the neighbors. Even with this efficiency, if we did that for 100 or 1,000,000 points, each query is going to be really slow. So it's an analytical job. It runs the MapReduce. And so what happens is it uses the Hilbert curve as a partitioning strategy instead, right? So my row keys, if people are familiar with MapReduce, are my map key is the cell ID, right? Now I've taken it and said anything that occupies that same cell is going to be reduced together, right? And so and actually with the Spark stuff we've done, we actually have a partition strategy with Spark as well that will actually use the Hilbert curve to take a simple feature and partition it based on its locality. So I hope that answers your question. Another question?
So how do you maintain those tiers of curves for rapidly changing data?
The question is, how do you maintain those tiers over rapidly changing data? So I'm not sure I completely follow. So,
It sounds like there's multiple levels of
right,
indexing.
right.
So if you have rapidly changing data where maybe, I don't know, adjusting those scales or other tiles.
So you're talking about data that might maybe grow, or I mean, like you might have a polygon that decides to grow, right? Change the actual geometry,
Think like telemetry data.
right? Because so when I think of change, I'm thinking that actual geometry is changing, right? Versus a new unique transaction, which may be at different tiers, right? Right. So, if you're changing an actual feature, right, and changing the geometry, then that is a removal and an add, right? It has to be, because right, it's you're basically re-indexing it with a new. But if it's a new transaction and it's just another insert, right? Gonna make sense? Does that answer your question? Okay, I got 1 more minute, so 1 more minute, 1 more question. Up, in the back.
You're saying this is n-dimensional. Is there a limit to that?
The question is there a limit to the number of dimensions? I would say, on a theoretical level, no. On a practical level, we haven't come up with one, but we also haven't worked past 5 or 6 dimensions. So I think, the problem with the n-dimensionalized space is that if you can think about it as like if you have at least one long dimension, right? And I'm using the cube. I'll use the cube, for example, on time. It's nice if these things are fairly square, right? But if you have, let's say, a query that's where you have a long stretch, right? Like maybe I'm searching a city block over a year, and there's a lot of data there. And then basically you can imagine that search space is this really elongated rectangle cube, right? And so what happens is you can picture the curve sort of going in and out of that curve. So it creates a lot of ranges, right? So the initial range computation time is long, but once you've got the ranges, then going over to the BigTable and letting it run on those ranges is very fast. So what you find is when you're starting to get into those big dimensions, you start finding a little bit of lag on that decomposition if your search space is long. So it's really about your queries, right? What you want to do is you obviously want to have your queries to take advantage of this. You want your queries to be fairly square. Does that make sense? So that's all I have time for. Thanks.